Welcome to What's New in C++23. My name is Cy Brand. I work as a C++ developer advocate for Microsoft, and you can find me on Twitter at TartanLlama. Before I get started quickly, we do have a bunch of people here from Microsoft, both attending the conference virtually and in person. So we have a booth for the first couple of days, which you can come along and chat to us, let us know your thoughts. We also have a channel on Discord where you can come hang out. We do have a survey, as with every year. It would be great if you could fill that out. It really helps us to work out what you folks all want us to do. So without any more ado, I'll get started. Now, if you're looking for what's new in C++23, you might go to some reference page like CPP reference and find a list, maybe something like this. And don't spend too much time trying to read this. This is all great, if you want to go through every single feature step by step and say, okay, here are the ones I'm interested in. I can go and read the papers. But it's a lot of information. It's hard to work out exactly what will be of use to you, exactly how to understand all of the standards papers and whatnot. So I want to make a presentation which is clear, understandable, shows you some of these features in use in a fun way. And I have 3 cats, so I thought I will use my cats as demonstrations. So my 3 cats are Marshmallow, Lexical Analysis Cat, and Milkshake. You can maybe guess which one's my kid named and which one was named by me. I think these pictures also kind of show their personalities quite nicely. Lexical Cat she is like the cattiest of all of them. She looks like something out of a Studio Ghibli film or something. Whereas Marshmallow has never had a single thought in his entire life, and Milkshake looks like she's just a chaos demon who wants to destroy the universe. But before starting this, this presentation is trying to condense C++23 into 60 minutes. I thought, could I do it in 60 seconds? So I wrote a little silly song about C++23. Please do let me know in chat if you cannot hear the sound. We did test it, but it's been a bit patchy. So here we go. Hey Marshmallow, do you want fed or do you want to know what's new in C++23? The second one? Ah, okay, I got you. And where you convert the member functions of a class. I counted to acceptance of your errors or massing. Now it's optional because brevity with these new operations. You can now index containers from multiple dimensions. There's a way to convert all your ranges into a container. And a coroutine that's written by the standard of maintainers. If you're simple, make you try it. If you think you're abstainers. It's a whole new better language and I cannot make it plainer. A bunch of stuff in C you can use where you're compiling. Writing ranges with informative will surely leave you smiling. And then input still will make your builds go faster than electrons. You can write standard out of last without those awful chevrons. These are the only ones which I could fit in 60 seconds. For now I have to run because the empty couple beckons. All right, so that is a bunch of C++23 features in 60 seconds, and now we can spend the rest of the presentation delving deeper into this. All right, so I said this would be all with my cats, and here we are getting started. So say I have 3 treats which I want to give to my cats: toy, chicken, catnip. One thing about my cats is they're not very good at sharing. If I give one of them a toy, the other ones are probably going to want toys as well. If I give one a piece of chicken, the others are probably going to want it too. So I can't get away with just distributing these amongst my cats. I'm going to need to triplicate them, make sure that I have 3 toys, 3 chickens, and 3 pieces of catnip, and maybe put these in separate containers so they don't get all mixed up. So what I start off with is something like this, just a 1D range of toy, chicken, catnip. And I want something like this, a 2-dimensional range of 3 toys, 3 chickens, a piece of chicken, 3 bits of catnip, so that I can distribute these amongst my cats. Now, how do we write this in C++? Let's do this step by step. We'll take a few steps at it. So we start off with this, our 1D range. And maybe to start with, we can just expand this out, triplicate every element. Note, this is still a one-dimensional container. Just every single element has been triplicated. Now, as far as I'm aware, there's not a range adapter in the standard library which exactly does this, but I could write one of my own, maybe call it repeat range n or something, where you give it a number and it will repeat every single element that many times. So now we want to group these into subranges. And there is something in the standard library now for this. It's called stdviews chunk. So I can say I want to chunk up my range into chunks of size 3. And we'll get exactly what we have here. Now this stdviews chunk is a new feature in C++23. Every new feature, I'm going to have a little star next to it so that, if you go back over these slides, you can quickly see where the new features are. In addition to stdviews chunk, there's also stdviews chunk by, which instead of taking size of the chunks, it takes a function and will group up your elements into the ones which return the same value given this unary function. So I'll also have the things which didn't quite fit into these examples in little boxes like that. And my phone is going to sleep, but there we go. Okay, so we've got chunk. And now say we want to print this out. We're going to write this out to a standard out or to a log file or something like that. So we could first put this into a variable. Let's just call it chunked for now. And then we want to print this out in C++23. We can just do this. stdprint, these little braces, and then chunked. Now this is actually using a couple of new C++23 features. It's first using stdprint, which is kind of like stdformat from C++20 based on formatlib, which is a very popular open source, like Python style, type safe, fast formatting library. But instead of formatting out to a string, it formats out to a stream, standard out by default. The second new feature is that formatting ranges wasn't a thing in C++20 format. You could format built-in types and things which had been customized for streams, but ranges didn't have their own formatting code. So now we can just say stdprint, give it our range, and it will print out something like this. Just square braces and all of our elements. There's a question in chat. Generally putting questions in the Q&A is better than the Discord chat in case my phone dies or something. But the question is how to redirect where stdprint goes. It can take an argument of a stream. Okay, so say now that we want to reuse this code. Maybe we don't want to just chunk up our treats. Maybe we have some other things that we want to chunk up, or something completely different, unrelated to cats. We would want something like this. Say, take our range and then say, repeat in groups of 3. And that will do the whole repeat range and then chunk. So how could we write this? One option is by making it a closure, saying we have a repeat groups, which is a lambda which takes a single size argument, and then this returns the composition of repeat range n and chunk. Now notice in particular that there's no range in here. We're not piping a range into repeat range n and then chunk. We're just composing these range adapters together. You might see this referred to as point free style. And this is a new feature in C++23. There's some machinery which makes it a lot easier for us to do this. Showing you exactly how the machinery works is a bit more involved. I do have a Godball link there if you want to go check it out. But it is now a lot easier than it was in C++20. And then maybe we take this code and we write it and we realize that this lambda is not being inlined everywhere for some reason. Maybe we could write always inline on this lambda, because as of C++23, we can now add attributes to lambdas, which is kind of cool. It's unlikely to make a difference in a case like this, but just to show you it's now possible. Okay, so we've given our cats some treats. Maybe we've now done some training. We've made it so that they don't have to have their own stuff. We can share the treats amongst the cats. Let's go back to our treats, our toy, chicken, catnip. And now we want to distribute these evenly amongst my cats. So we have marshmallow, milkshake, and lexical cat. How do we make a range of pairs of these where marshmallow gets a toy, milkshake gets chicken, lexical cat gets catnip? Well, a quick way in C++23 is to use zip. This takes any number of ranges, it's variadic, and when you dereference an iterator into this range, you will get back a pair or a tuple of the relevant elements from all of these ranges. So this will give us marshmallow and toy, milkshake and chicken, lexical cat and catnip, just like this. So this will be a range of pairs. In addition to std_views, there is std_views zip transform, which instead of giving you back that pair or that tuple, you give it a function and it will call that function with that pair or tuple and yield back the result of calling that function. But what if we want to put this into a container? We could, loop over this and write it into an unordered map or something like that. But in C++23, we can now use std_ranges 2. This is something I really, really missed from C++20. If you used range v3, you kind of use this thing all over the place, right? You just want to take a range and collapse it into memory because you're going to use, you want to pass it to something which requires it to be contiguous, or you just want it to be in a container. And this is what std_ranges 2 allows you to do. It'll work with vectors, it'll work with unordered map, whatever. Note that I did not have to say what the key and value types of the unordered map were. I could do if I want it to be explicit in the code, but it will just work it out for me, which is very cool. But then maybe I take this and I run the code and I realize that I'm having some performance issues. Maybe I'm getting a lot of cache misses because std unordered map is basically a vector of linked lists under the hood. It's not a very cache efficient data structure. Maybe instead I could switch to using flatmap. Flatmap is a new container which splits up our keys and our values into 2 contiguous containers. It doesn't use hashing. Lookups are a binary search, which I would guess would fall back to linear search for small enough n, but this can be a lot more cache efficient than the kind of implementations which are required for std unordered map. But then maybe we decide, our cats have done a really good job with all of their training. Maybe we do want to give each of them their own toy and chicken and catnip again. In that case, we could use the new std_views Cartesian product. This will take the Cartesian product of our cats and treats, giving us marshmallow toy, marshmallow chicken, marshmallow catnip, milkshake toy, so on and so forth. I worked on this paper, and it can be very handy for those times where you want to do like a nested loop, essentially, on a bunch of containers, but then use that result for further operations, like putting them into a container or giving them to a filter or some other range adapter. It comes in very handy. Let's switch gears a little bit, get back onto training the cats maybe. So we want to have a little game we play with them when we give them a treat. We don't want to just feed them. We want to offer the food, and the cat is going to hold out their paw and we'll give it a little shake, and then the cat will open their mouth and we can then feed them. And maybe they make a mess. If your cats are anything like mine do tend to make a lot of mess. So all of these functions return optionals. This is because we might not get what we expect. We offer the food, maybe we don't get a paw. Maybe the cat just forgot. It's not been trained well enough yet, or it just wants the food. It doesn't want to give you a paw. So it's optional. Maybe we get a paw back, maybe we don't. Then when we go to shake the paw, maybe the cat gets bored and just wanders off. Maybe it doesn't open its mouth, so this is an optional. And then when we feed the cat, maybe miraculously it doesn't make a mess. So this is why it's optional. So we've got this chain of operations. Now, how do we code up that little game of offering food, shaking hand, feeding, keeping into account that all of these might return nothing, in which case we just want to stop and back out? Well, we could do something like this. We offer the food, we get back an optional, we check if we got nothing. If so, then we return null opt. We shake the paw, we get back an optional, we check if we got nothing, we return null opt in that case, and then we feed. And you'll notice that this gets kind of noisy. It's not too bad for a function like this, but as you add more and more and more things, this becomes more and more unwieldy. You have to have all of these checks interspersed with the actual operations which you're doing. Maybe you can find other ways to write this, right? Like you could use the if initializers to compress the vertical space at the expense of some horizontal, but it's still the same kind of thing, right? We're having a lot of syntactic noise because we're having to manually do this checking over and over again if we got an empty optional. And what we really want to do is just say, okay, offer the food, and then shake the paw, and then feed the mouth. And if at any stage we got back an empty optional, just return that back and don't bother about checking it manually. And C++23, we do have this option. We can say exactly that. Cat.offer food, and then shake the paw, and then feed the mouth. And if at any point we get back an empty optional, then that just gets returned, and the further calls to and then are no ops, essentially. So this is part of the Monadic interface for std optional in C++23, which is a paper which I wrote. And this is something that I use all the time in my own code when I'm dealing with optionals and expecteds and all that kind of stuff. It just makes a lot of use cases much nicer to reason about without having all of this syntactic noise. There's also a couple other functions which come with that. Std optional transform, which is when you want to change the value inside an optional, but only if there is one. And then or else, which is when you want to call some function if an optional is empty. But there's maybe a bit of a problem here. If we come back to our interfaces, I did mention that there were a bunch of different reasons why these things could return empty optionals, right? Cat gets bored, cat has forgotten its training, cat is too excited about getting fed, all of these things. And this interface gives us no real way of working out what those reasons were. We just get back, oh, empty optional, something went wrong. So what if we want to get this information out of our interface? Well, one option is to use std expected. Std expected is kind of like optional, but instead of you get this thing or nothing, it's you get this thing or something representing the error or the unexpected state, something telling you what went wrong, basically. And this gives us that information which we wanted. Std expected, I believe, doesn't yet have that same Monadic interface. I think there's a paper in flight. I don't know if that particular part is going to make C++23. If anyone in chat knows, you can say. But let's have a look at how you might go about implementing expected. So let's look at specifically just the value function for now. So to get the value out of a std expected, you can call the dot value function. And this has 4 overloads for when the expected object is a const L value, a non-const L value, const R value or a non-const R value. And this is so that, if we call std move on an expected object and then call dot value on that, then that dot value should give us back an R value. Or if we call dot value on the result of a function call where it returned an expected object by value, then that dot value should give us back an R value. And we want to conserve the constants as well. But this gets a bit unwieldy again. It's not too bad for this function. It's fairly simple, but expected has a lot of member functions, and you have to do this kind of pattern a lot of times, and some of the functions get more complex, especially when you include that monadic interface for std optional, which we showed. So we get this quadruplication of code, which is, you'll know how bad quadruplication of code can be. It can be a maintenance headache. It can hide bugs. It's harder to test, all of this kind of stuff. So what C++23 lets us do is write a single function template to do all of this stuff. So how to read this is, you see the single function argument on this value. It has this keyword before it. And that says that, okay, this argument, this parameter even, this is special. This represents the object which this member function has been called on. So previously in C++, we call the function on some object, and that magically turns up in this slot inside the function. So we can refer to this, and that will be a pointer to what's called the implicit object parameter for the member function. What deducing this lets you do is make it explicit. Maybe a better name for the feature is explicit object parameters. And the most important thing here is that it lets you make it a template parameter, or rather make the object's type a template parameter. And that lets us deduce whether it's an L value, an R value, const, non-const. So now we don't have to quadruplicate the code. We just write a single template and it does everything for us. And we can use std forward inside our member function in order to conditionally move if we were called on an R value. There actually turns out to be a lot of magic which falls out of this. When I was one of the 4 co-authors on this, myself and Barry Revson were writing one paper for kind of dealing with this situation where you've got 4 methods you're wanting to write when you only should write one, really. And it turned out that Gasper Asman and Ben Dean were writing almost entirely the same paper, but for a different use case to do with deducing whether a closure object was an L value or an R value. So that's another one of the use cases, working out if you call a closure, am I an L value or an R value? Can I move my captured state out of myself? It also happens to let you do recursive lambdas. It lets you do the curiously recurring template pattern without having to template yourself on the derived type and do that weird static cast thing, because you're a template parameter now, this could be deduced to a derived type, which is kind of interesting. It's one of these things where we just designed this feature and then like, oh, this lets us do this, and that's kind of cool. I've got a couple of questions. Alex says, does this invalidate the concept of only pay for what you use? I don't think so. I mean, it's a template, so you're only instantiating the overloads which you're using, which I don't want to get into too much. It actually solves a hole in the C++ language which you cannot solve right now. The fact that you have all these overloads which get involved in overload resolution even when they shouldn't be. So I don't think it does invalidate the concept of only pay what you use. If you have any specific reasons you think that, you can either just put them in Q&A or drop them in chat, and I can follow up on them. Another question is, any sound reason why/when you would ever want to overload const ref ref? So const ref ref does come up in mostly generic code when you're doing a bunch of operations on types which you don't necessarily know a lot about, and some of them are returning const and some of them are getting moved from or forwarded, and you end up with const ref ref at some point. And then if you get to that point and you call dot value, you kind of want to preserve that, or something might go wrong. So it can be a safety issue sometimes. That's all I have on deducing this right now. If you want to know more specifically about deducing this, you can go and watch Ben Dean's talk from C++ Now. I think it's really, really good. It shows like a bunch of different use patterns for deducing this. All right, back on to feeding our cats. So we want to feed Marshmallow a bunch of treats. We don't care about how we get these treats. We just want to get treats and give them to Marshmallow. He's a very good boy. So we could write code like this. We could get a treat generator from somewhere, and then we just treat this as an infinite range of treats. So I just say, take 10 treats from this generator and then feed them all to Marshmallow. And this std generator is a new feature in C++23. It's the first standard library coroutine which we have. In C++20, we got the language support for coroutines, but none of them shipped in the standard library. Now we have std generator. Now how this would look under the hood, let's look at the implementation of this make treat generator function. Okay, so the important part here, well, one of the important parts is the return type. This is how you customize coroutines in C++ by picking a return type which tells the compiler what I should do in certain coroutine-like contexts, which we'll see in just a bit. So this returns the generator of treats. We begin with some number of treats, let's say 50, and then we have an infinite loop. If we have run out of treats, then we go and get some from the shop, and then we just decrement the number of treats we have and co-yield one back to the caller. So a few things here. Co-yield is part of the coroutines feature from C++20, and co-yield itself doesn't have a built-in semantic meaning. That's the generator return type. That's what tells the compiler what you should do when we write co-yield. And so std generator will deal with storing this treat somewhere so that the caller can retrieve it. So when we hit this co-yield line, this coroutine will be suspended, the treat will be passed back to the caller, and then the coroutine can be resumed later when we ask for a new value. So this looks like an infinite loop, which will just keep on going and keep on going. But because of this co-yield, the coroutine will be stopped and resumed later. And the function of this really is to not have to deal with the state ourselves. Like we've got this number of treats. If you were not using coroutines for this, there's a few ways you could deal with it, right? You could pass it around as a parameter. You could allocate it on the heap and just store a pointer to it somewhere. You could use a closure. There's a bunch of different ways you can deal with it. But with coroutines, we can write what looks essentially like a regular function, but which has state carried over from every time you resume it. And this means that we can think about the implementation of our coroutine without having to deal with the state manually. It's all handled by the implementation, which can be very, very handy. Don't see any questions, so I'm going to move on. Now, I want to have a way to get cats from my API. Like we need a way to get a cat so that we can feed it, so that we can pet it, all of this kind of stuff. Unfortunately, the API I'm using is a very janky C API for just that getting cats part. Like something like this. We have a get cat function, which takes a cat pointer as it's an out parameter essentially. So when you pass it pointer to pointer, it will allocate some cat and store the resulting pointer in that C parameter. Then you give it a color as well. This really should be an enum, but for some reason lost to time, it's just an int. Then there's a delete cat function for reclaiming the memory, which was allocated by getCat. But we want to use these functions in a safe way, right? We like to not have to remember to call delete cat, because it turns out to be a surprisingly difficult problem to make sure it's called once and exactly once for every call to get cat. So what we want is, of course, a smart pointer. Now, one way to use smart pointers with something like this is to make a deleter type, which I'll call cat deleter, and this will just call delete cat. Now, one slight improvement we can make on this in C++23 is we can make this call operator static. So one thing about the old version, when the call operator was just a regular member function, is that if this call is not in line somewhere, if it's on like an ABI boundary, then we need to pass an instance of cat deleter as a parameter. And this will be passed by reference. So you're storing what's essentially useless data on the stack, because we don't use cat deleter for anything. It doesn't have any state. It's just used for its type. We have to store this on the stack and then pass its address in a register. It's just stuff which the compiler has to generate, which is not ever going to be used. So we can instead mark it as static, and now we don't have to deal with that extra implicit object parameter when we call this operator this call operator just for deleting the cat. So now we want to call getCat. How do we do that and have it correctly managed by the unique pointer? It could look something like this. We make a unique pointer. We make a regular raw pointer to a cat. We pass the address of that pointer to getCat, and we do a static cast to int from some color, and then we call c.reset on our smart pointer to reset to take ownership of that raw pointer. This is it's okay that this is kind of error prone. You could forget to call a reset. It's just a bunch of code we have to write to call a single function to get a cat. It's not very fun. What we can do in C++23 is this. We've got a couple new features here. The first one is stood out pointer, which is a way of dealing with situations where you have a pointer the API which has out pointers and you want to manage the result in a shared pointer. You just pass that shared pointer as a stood out pointer, and it will deal with all of that resetting nonsense itself. Then instead of having to do that static cast to int and worry about the width of our enum or whatever, static cast to int is just kind of ugly as well. This is much nicer, just saying, give me the underlying integral representation of this enumerator. And that's it. So these are two little handy functions for dealing with those kinds of C APIs and not having to avoid our smart pointers, not having to avoid our scoped enums, all of that kind of stuff. There's a few additional features which are adjacent to these. Stood in-out pointer is for the same kind of situation, but when the C interface is relying on the previous state of the unique pointer. It's both an input and an output, the output parameter. Then is scoped enum is a type trait which tells you if something is a scoped enum as opposed to an unscoped one. Then, since we're talking about unique pointers, you can now use unique pointer in compile time context, some compile time context, which is very cool, I think. While we're on the subject of unique pointers, so we're using unique pointers now to manage our cats. This comes with some additional considerations. Say that we have some cat action type, which represents some action a cat can take at some point in time. And it will have a name like make mess or play with toy, that kind of thing. And it'll have an action which doesn't take parameters and returns a mess. And this is stored importantly as a std function. Now, how do we use this? So we've got our cat unique pointer, we've got our cat action, and we're going to try and fill in this action member function. So one way we could do that is by having a lambda which std moves from the cat pointer and captures the result. So this is moving the unique pointer, moving the ownership of the unique pointer out of the enclosing scope and into the closure. But this doesn't compile. The reason being that std function does not accept move-only types. And this closure, by virtue of having a unique pointer as a capture, is a move-only type. So this won't compile. If we want to do essentially this, but we also want to support move-only types, then we could use std move-only function in C++23, which you might be familiar with. This got called unique function in a bunch of places. There have been open source implementations going around for several years for this kind of thing. But now we have a version in the standard, and it's called std move-only function. Okay, so we've got our kind of janky C API, which we're wrapping with unique pointers. Maybe we want a slightly nicer interface for getting our cats. So say we've got our color enum with black, tortoiseshell, ginger, calico. I don't have a calico cat. I do have those first three. And then we have a function to get one of my cats from the relevant color. So how could we implement this function? We could use a simple switch statement. If the user passes black, we return lexical cat, ginger, marshmallow, tortoiseshell, milkshake, and otherwise we can call std unreachable. You might be familiar with built-in unreachable, which is in GCC and Clang. MSVC has a similar kind of thing. Basically what it does is say, hey, this branch is undefined behavior. And the optimizer can say, oh, okay, based on that, I can make other assumptions about this function and even the enclosing scopes and caller based on what I know about this branch. So that in some cases, the optimizer can really go to town on your code just by knowing that some branch is undefined behavior. Now, one thing that my cats like to do is sit around in boxes. I always have boxes just sitting around. So I like to model them. I like to monitor what cats are in what box. I actually have specialized hardware for it. So I represent this as a single array of optional cats, 2 by 3 by 4 matrix. It's a stacks of boxes. And I can access this as a multi-dimensional index using mdspan. Std mdspan is a new container. Well, not container. Is it technically a container? I can't remember. But it's a new C++23 feature, which is kind of like a span, but it's multi-dimensional. So you give it the type of the elements and then the extent, which should be how to group the underlying range into multiple dimensions. And now we can refer to this like so. This 0, 1, 1, that's inside square brackets. Now we can write multiple indices inside square brackets. This is one of those like really small usability features, which if you've used similar kind of multi-dimensional containers or spans before, they always would use like overload the call operator or have multiple, like they would return a proxy and have multiple calls to the index operator or something. It's not nice. This is much better. This is what we've always wanted, and now we have it. If you want it to be super explicit that these are std size t indices for whatever reason, you could use the new std size t literals. You wouldn't do it in this case. I just wanted to show you the literals. There are cases where this is useful. Is the MD array operator overloadable? I don't actually know the answer to that off the top of my head. You'd have to check the paper. If someone else in chat knows, please do drop in the answer. All right, so we've got our representation of our boxes. Now we want to have our specialized hardware send this information to my regular desktop computer. I'll do that with a couple of functions. I have to pack up this data into some wire format, which I can then dispatch over the network to my regular computer. So my dispatch box data is going to pack up the data from my box span, and then it's going to send this over the network. But I know that my special hardware has a different byte order than the network, so I need to do a byte swap operation. We now have a standard way of doing that in C++23, std byte swap. Previously, you might have used compiler intrinsic or just a regular function. The compiler intrinsic is, of course, not going to be cross-platform. The regular function might not be optimized as well. Std byte swap on x64, for example, can compile down to a single instruction. So this gives you the best of both worlds in portability and performance. Now, how about packing this box data, taking that box span and generating some wire representation of this? Now, my specialized chip actually has a built-in instruction for this. But one problem is I also want to be able to do this at compile time for some certain use cases. So I cannot call that intrinsic at compile time, which is a problem. How do I make sure that at runtime I use my specialized intrinsic, and at compile time I do something which is actually valid at compile time? Well, in C++23, I can use if const eval. In the first branch that says, if I'm being run at compile time, do this. I can do some costly context per friendly algorithm. Otherwise, if I'm at runtime, then I can use my specialized hardware intrinsic, and this will do the super fast runtime version. This is very similar to std is constant evaluated from C++20. It has a few improvements, such as people like to say if context per std is constant evaluated, which is subtly wrong. It also fixes a few other problems. This is just better. If you have to ask whether you're being run at compile time or runtime, if const eval is where to go. And if I'm implementing this costly context per friendly algorithm, I could now use some of the utilities in CMath for doing this. If you've ever tried to like call, I know, log at compile time, it doesn't work. Now it does. Very handy. But sometimes this stuff goes wrong, right? I tried to send this over the network. Maybe my computer is not reachable. Maybe I had some hardware interface problem. I don't know. A bunch of stuff can go wrong. So what I have on my little chip, which is monitoring my boxes, I have a little display, which I can use for debugging. And there's a function called getDisplayBuffer, which just gives me back a buffer that I can write into. It's just like a memory mapped IO thing. And when I write text into this buffer, it will show up on my little display. Now, how can I nicely write characters into this buffer? Well, I'm going to check if we've got an error. This is returning an optional or an expected or something. And then I want to get my display buffer, and I want to create a O-span stream from it. This is a new feature in C++23, and it lets you create an output stream from an existing buffer. So I could do something like create a string stream and then copy that data into this buffer, but using a no span stream says, okay, I'm going to use this existing buffer for all of these O-stream operations, which can be handy when you've got a fixed size buffer which you're writing into and is already allocated. And then maybe I want to write this current stack trace out as a kind of debug view. I could do that with std stack trace current. So the std stack trace functionality, there's quite a lot of API surface to this thing. So I don't want to go too much into it. You can go look at the CPP reference or something, but you can get the stack trace, you can walk over the frames, you can do basically the kinds of things you would expect from this, just visualizing and manipulating the current stack trace. My specialized chip also supports sending some commands over the network. These commands are all semicolon separated and can make it do things like reset or show the current number of boxes, things like that. So if at my regular computer, I have a bunch of commands I want to send over, I've got like a span of string views of commands. How do I make this semicolon separated string to send over the network? Well, now I can just say, take my commands and join them with semicolon. Std views join with is a new range adapter and lets me do exactly what I would hope. Just stick semicolons in everywhere and don't have a dangling one on the end. And then I can dispatch this and get back a response. Maybe I know there's been an error if this response string contains the word error. So how do I check if a string contains some substring in C++? Well, of course, you use .find and compare it to std string npos, which is just we've had to deal with that for so long. Now you can just write contains if response.contains error. It's just better. It's taken a long time, but we got there, and then we can handle our error. All right. So the last example before this presentation goes to bed, and before my cats go to bed, I like to get them to count sheep. So let's write a function to help them count sheep. I could write get a vector of numbers to count of just 100 zeros. Then I could use the new stdranges Iota algorithm to just write 1 to 101 into this vector. In case you're wondering, didn't stdranges Iota get into C++20? It's slightly different. Stdranges views Iota, or stdranges Iota view, was in C++20. That's the lazy generating range adapter. This one is eager. This is an algorithm. You give it some container and it will immediately write all of the subsequent values into that range. And then maybe we want to pop all of these numbers off. We could just like shift the vector down and pop every the front value off every time. So while numbers count is not empty, then we're going to shift our vector to the left by 1 and then count the number which we just shifted off. So shift left just takes some range, shifts everything to the left by some number, and gives you back everything that it shifted off the end. And then, as you might imagine, there's also a shift right function, which does the same, but shifts everything off to the right. Now, last thing is, how do I get std vector, std range of shift left, all of this stuff into scope? I use hash include, right? But now I can use import std. So import std is modules for the standard library. There's 2 modules, there's std and there's std.compat. The difference being that if you use std.compat, you will get all of those C names into the global namespace. So if all of your code is just using bare, printf, malloc, whatever, then std.compat will import those names into the global namespace. If you do not use std.compat, then it'll be stdprintf, stdmalloc. So those are all of the examples which I wanted to show you. Everything on one slide. I don't need to really read this, and I'm certainly not going to read everything off the slide, but if you want to take a picture or whatever, then this is all of the new features in C++23, which I talked about today. There are some things which I didn't have time for or didn't think fit very well. These are just some of them. You can ask if a range starts with or ends with some subrange. Std_ranges fold is a more generic version of std_accumulate. Std_view slide gives you a sliding window over a range. Views adjacent is the same, but with a compile time sized range. Invoke R is like std_invoke, but you tell it what return type you want the result converted to. And then there's also a way of trying to find out if a reference is going to be dangling. There's also a bunch of other stuff which I didn't put in this slide nor in the talk, but I think that all of this covered most of the interesting features to the majority of C++ users. And with that, thank you very much. We still do have time for questions, so please do write in any additional questions into Q&A. And as a reminder, we do have the Visual Studio channel on Discord, and we have our survey, which you can go fill in, which helps us a lot. We also have a bunch of other sessions over the next few days. I have another session on Friday of what's new in Visual Studio 2022. And yeah, questions. Did ranges 2 make it in? Yes, ranges 2 did make it in. I did have an example of that. Where was that? Here. There. Piping std_view zip into std_ranges 2 to change the lazily generated range, just dump it into a container. So yes, std_ranges 2 did make it in. Mikhail in chat has said that we found that the multidimensional span does have operator overloading stuff in it. Thanks for checking that. We've got about 7 minutes left, so still time for more questions. If any of you have favorite C++20 features that you want to drop in chat, that would be cool as well. Grace asking, is the Visual Studio channel invite only? You have to go to the, it's one of the special interest groups. So you have to go to the register or registrar room and then press the little tick box on the Visual Studio channel, and then that will get you added. I think it's called directory, the directory channel under special interest group. My personal new favorite is deducing this. Alex says, seems like std_generator is a neat new feature for avoiding having to create a magic static in a function scope and reusing it. How does std_generator maintain its statefulness? What is the runtime cost? Okay, so std_generator uses the C++20 coroutines functionality, which nominally will allocate the frame for the coroutine on the heap. Now, this can be, in many cases, elided. I think, do people call it Halo? I can't remember what it stands for. But yes, the allocation for the state can be elided if the compiler can make sure that there are certain lifetime guarantees of the coroutine with respect to its use. So in order to, I don't think there are any facilities yet to detect whether a particular coroutine has had its, they're called activation records, I think, whether it's had its activation record elided or not. But you can always check the assembly, things like that. So yes, there can be costs to using coroutines. I think I did do some benchmarking like a couple of years ago on simple generators versus ranges, and the ranges were getting optimized better. But this kind of stuff, coroutines have not been around for super long time in the C++ standard, so compilers will continue to get better at optimizing them.